So for the steel shaft here, okay, these are the diameters and these are the cross-sectional diagram. So for steel, it is at the outermost layer. Steel is the outermost layer. So the big diameter and the small diameter is this one. This is the big diameter for the steel. All right, and this is the small diameter for the steel. Okay, can you see the difference? So first of all, in order for you to find the torsion stiffness for the steel shaft, you have to find the steel shaft's big diameter and also small diameter. Okay, so the big diameter for steel shaft, since steel shaft is at the outermost layer, so the big diameter is 25, and the small diameter for steel shaft is 15. This part, all right? So remember the length for both material is the same, which is 5 meter. So use this formula right here. Kp equals to pi g over 32L times d to the power 4 minus small d to the power of 4. And then you get the answer to be what? Kt, I'm going to put as KTS, all right? Torsional stiffness for the steel equals to pi times the G. The G for steel is 80 times 9, 80 times 10 to the power of 9 EA. So put it here, 80 times 9 times 10 to the power of 9. Okay, and then divided with 32 times the length, 5 meter. And then times with the difference between the big diameter and the small diameter to the power 4. So the big diameter here is 25 cm. When you substitute, make sure you substitute in the SI unit. So the SI unit of 25 cm is 0.25 meter, and the SI unit for 15 cm 0.15 meter. So the big diameter 0.25 to the power of 4, all right, minus with a 0.15 meter to the power of 4. That's all. Okay, this question over here is very easy actually. So you can already find your torsional stiffness for the steel shaft, okay, which is 5.34072 times 10 to the power of 6 Newton meter per radian. All right, this is for the steel shaft. Okay, now let's try and do for the use the same formula, but now you have to find for the aluminium. Okay, remember, use the same formula, only the diameters are the different. Now for the aluminium shaft. Okay, so what are the difference between the steel shaft and also the aluminum shaft? Only the got two difference on the diameters and also the G, more or less. All right. So try and substitute that. Change first. I'm going to change this first. Okay, for the G for aluminium is 26 GPa, right? So substitute over here 26. And then for the diameters, aluminium is in the inside, right? Steel is at the outermost layer, aluminium is underneath the steel. So the big diameter for aluminium is this one here. This is the big diameter for aluminium, and the small diameter for aluminium is the hollow part here. Okay, which means over here, the one that we want to find is this one. All right, which is the big diameter for aluminium is 15 cm, and the small diameter for aluminium is 10 cm, 0.1 meter. So again, just substitute that back into the formula. (15 cm, 0.15 meter, and also 10 cm, 0.1 meter. So just substitute those values inside the very same formula, and then what will the answer for the torsional stiffness for aluminium shaft will be? Okay, once you calculate that, you get the value for torsional stiffness of the aluminium to be 0.207395. Okay, times 10 to the power of 6. Times 10 to the power of 6 Newton meter per radian. Okay, now question 1 is the torsional spring stiffness of the shaft, of the entire shaft. Okay, since the shaft is made up from 2 different materials, now you already have the torsional stiffness for each material. So the thing that you want to do now is find the equivalent K. So try and find the equivalent K for this one. In order for you to find equivalent K, if you have multiple Ks here, you have to know the configuration of the stiffness for the entire shaft. Is it parallel or series? Remember, if one of the shaft moves, okay, or elongates when it applied force or pressure onto it, will both shafts made up from both different materials move at the same pace, at the same elongation, or differently? You have to know that first based on the diagram. Since they are attached to each other, so the elongation for both will be the same. Okay, so since both elongation will be the same, so remember, since they are attached to each other, right? So since both elongation is the same, you can assume it to be parallel, because why? If I draw it this way, let's say this is K1 and this is K2 and this is load, for example. So when a load is applied on these two springs, okay, so they will have the same displacement because they are being pushed together at the same time, okay, because they are attached to each other or they are on top of each other, like last time the question is from the first tutorial question that we had. All right. Okay, so since they have the same, they are being pushed together at the same time, at the same point, okay, or they're attached to each other, so the displacement or the elongation are the same. So we can draw the schematic diagram for the spring to be like this. Okay, at one point they are attached to each other, and if load is being applied, the displacement for both will be the same. Okay, so if I draw it this way, you can see it is actually you can actually see it is actually parallel. All right, so in parallel configuration, the equivalent K is, you have to add both K's if it is equivalent. So basically, K equivalent equals to torsional stiffness for steel plus with torsional stiffness for aluminium. And for this, you get your value to be okay, I'm going to write it down first. All right, in the end, your equivalent K is 5.54811 times 10 to the power of 6 Newton meter per radian. This is the answer for the first question, for A, right? We've already settled for A here. Now let's try and find for B. Okay. So for B, the question asks you to determine the torsional spring constant of the composite shaft when the inner diameter of the aluminium, all right? If the inner diameter of aluminium tube is 5 cm instead of 10. A very basic, very simple question. What do you have to do if they change the inner diameter, the small diameter of aluminium from 10 cm to be 5 cm? They change the inner diameter, the small diameter for aluminium. So basically, you can just copy this back, okay, the one that you've already done to find the torsional stuff for the aluminium. Change it from 10 cm or 0.1 meter into 5 cm, 0.05 meter. That's all. And try to calculate everything back, and then you'll get your answer. Okay, very simple question. Try to do it first. Okay, so now when they've already changed the inner diameter or the small diameter for the aluminum shaft from 10 cm or 0.1 into 5 cm, which is 0.05, I just use the same formula again, just change the inner diameter from 0.1 meter to 0.05 meter. Yeah, everything stays the same, right? So from there, I can calculate everything back and get the value to be, the new value to be 0.2553 times 10 to the power of 6. All right. That is the answer for the new torsional stiffness for aluminium. So are we done here? Actually, not yet, because we have to, again, need to calculate for the equivalent stiffness. All right, we have to again calculate for the equivalent stiffness. Because just now we've already found equivalent stiffness for both by adding the torsional stiffness for steel and also torsional stiffness for aluminium. But now, since the torsional stiffness for aluminium is already changed, so you have to again find the equivalent stiffness back by adding the new torsional stiffness for aluminium with the torsional stiffness for steel. All right. So as easy as that. So just add both of them back together. So your new equivalent K, once you add both of them together, you'll get your new equivalent K to be 5.596 times 10 to the power of 6 Newton meter per radian. That is all for question 1.43.